In this video, we will learn to describe how fast or how slowly reactions happen, and look at things like the temperature and how they affect the rate of reactions. All chemical reactions start with reactants and finish with products. All chemical reactions involve at least some changes in chemical bonds and the positions of atoms, ions, electrons and nuclei. The modern world depends on a huge number of chemical reactions actually happening. But what is equally important is how fast or slow these reactions happen. And sometimes, even if a reaction can happen, we don't necessarily want it to happen. For instance, it's better if rusting is very slow because we want to hold on to bits of iron because its strength allows us to do very useful things. On the other hand, our bodies use enzymes to break down toxins incredibly quickly. If these toxins aren't broken down fast enough, we can get very ill or even die. But thankfully, chemistry is in some ways very reliable and dependable. When reactants turn into products, we can see lots of things changing, and we can measure many more, but some of these are more useful than others. For instance, if we wanted to measure how quickly you could eat a portion of French fries, we could do it in a few ways. Well, the easiest way would be simply to time how long it takes to eat the entire portion. Or we could express it by counting the number of fries we eat in the same time. And then we could simplify that number to see how long it takes to eat one fry on average. And another way we could do it would be to look at the mass of the portion and see how much mass we consume per second. When we calculate rates like this and simplify them, what we're doing is coming up with an average rate, which is equal to the change in mass or amount, commonly, divided by the time taken. We can use this average rate to compare one meal to another, and here we can plot how amount changes over time. We can do exactly the same with the mass, although they don't necessarily match up because one fry doesn't necessarily have the same mass as another. But either way, changes in amount and mass seem like a good way to assess a rate. Instead, we could try measuring how smell declined with time, or even take photos of the plate and see how much yellow there was. We could even try to assess remaining hunger. Some of these metrics are very helpful and will allow us to quantitatively compare one meal to another, but others are quite challenging and present problems that would be difficult or even impossible to solve. It would help if we didn't have to rely on something as personal as hunger or as difficult to measure as smell. This is why we'll most often see reaction rates expressed as changes in mass over time or changes in amount over time. Some chemical reactions can be incredibly slow, like the conversion of organic matter to coal and oil. Or they can be fast enough for us to observe at a reasonable rate, like a candle burning. Or they can be so fast they're an explosion, like the detonation of a hydrogen balloon. But what do we really mean when we talk about the rate of a specific reaction? Let's imagine we're burning some coal. Under ideal circumstances, the reaction of coal and oxygen in the air produces carbon dioxide. We can assess the rate of this reaction by monitoring changes in mass or amount, and in this case we're seeing a reduction in the mass of the coal of 3 grams per second. If this were the case, then we'd be consuming 8 grams of oxygen per second as well, although I won't go into the calculation for this in this video. Instead, we're looking at how the numbers relate to one another. If the reaction was working perfectly and we could measure precisely, we'd also measure we were producing 11 grams of carbon dioxide per second. The law of conservation of mass reminds us that the mass of a closed system cannot change if we're dealing only with chemical reactions, so it makes sense that the rate that the mass of reactants goes down is going to be equal to the rate that the mass of the products goes up. Now, what about amount in moles? Here, for simplicity's sake, I'm going to assume that coal is pure carbon, and I'm going to use the rounded molar masses for the elements to work out the amounts in moles. 3 grams of carbon is equivalent to 0.25 moles of carbon. So if we're consuming 3 grams of carbon per second, we're consuming 0.25 moles of carbon per second. 8 grams of O2 molecules is also equivalent to 0.25 moles of O2 molecules, so consuming 8 grams per second of O2 is equivalent to consuming 0.25 moles per second of O2. And we can do the same for our product, carbon dioxide, and demonstrate that producing 11 grams of carbon dioxide per second is equivalent to producing 0.25 moles of carbon dioxide per second. Using amount rather than mass gives us certain advantages because we can relate the rate of production or consumption of a component to its stoichiometric coefficient and molar ratios to other substances. We could express the ratio of rates like this, paying attention to whether the rate is negative, in which case we're consuming, or positive, in which case we're producing. But the convention is to just have the stoichiometric coefficients in a ratio, and remember that the rates for reactants are going to be negative and the rates for products are going to be positive. In this situation, it seems more helpful to talk about the rates in moles per second, but in industry, talking about mass per time is often more helpful. We could also do a similar reaction where instead of producing carbon dioxide, we burn coal inefficiently to produce carbon monoxide. If this happens perfectly to plan, we'll need twice as much carbon as before if we're using the same amount of oxygen. Just like with regular reactions that go to completion, if we've got a component we're only providing at a certain rate, we can consider it the limiting reactant. So here we're only consuming 8 grams of oxygen per second. So we'll be using 6 grams of carbon per second, and therefore we must be producing 14 grams of carbon monoxide every second. And if we convert the mass rates to mole rates, this is what we get. If you look closely, you should be able to see a pattern. We can see that the rate we consume a reactant or produce a product is in proportion to its stoichiometry. This makes sense, since if we're using twice as much carbon per reaction, we'll consume the carbon twice as fast. But all this is based on what we can measure. What do we actually understand about what's going on, and how can we use that knowledge to our advantage? The first question we need to answer about reactions and reaction rate is this: why do reactions happen in the first place? Collision theory suggests that reactions will only happen when particles collide with each other. If particles never touch, they can't possibly react. But not every collision is going to lead to a successful reaction. In fact, the air around us is filled with particles that are colliding and not reacting. The other necessary component is that there's enough energy in the collision in order to break bonds and rearrange particles. But even then, if a collision has the right energy, it may not be successful because the particles are not arranged properly. If they aren't in the right orientation, the energy won't be transferred into breaking the right bonds. This means that only when particles collide with enough energy in the right orientation will a reaction occur. We call the minimum energy needed for a reaction to occur the activation energy. Although it's not measured in this way, we can think of the activation energy as the energy required to break just the right bonds that allow the new bonds in the products to form. Armed with this information, let's see how we can put it to use by changing reaction rates. Collision theory suggests there's a few things that could be different to make a reaction faster. If we can find a way of making collisions happen more frequently, the reaction should be faster. And if we can find a way of increasing the energy of those collisions, the proportion of successful collisions should increase, so the rate of the reaction should go up. And lastly, if we can find some way to do it, if we can lower the activation energy, then we increase the proportion of collisions that will be successful. In this video, I'm only going to look at the effect of temperature on reaction rate, but I'll tell you a few others as well. We can take the typical example of a gas. If we heat up the gas, the particles will move more quickly. The faster particles are moving, the more often they will collide. And since they're moving faster, their collisions will be more energetic. If we do the opposite and cool the system down, the particles will move more slowly. This will result in less frequent, lower energy collisions. Although we generally depict this scenario with gases, heating up solids and liquids will also increase the rate at which they react. So, broadly speaking, increasing the temperature will increase the rate of reactions by providing for more frequent collisions with higher energy. And while we won't be going into the mechanics in this video, here are a few other factors that you could change to increase a reaction rate. For reactions involving at least one gas, increasing the gas pressure will increase the frequency of collisions and increase the reaction rate. And we see the same effect for solutes in solution. If we increase their concentration, the rate of reaction will increase. The more of them there are, the more frequent collisions will be. And for reactions involving solids, it's better that we have lots of small pieces with a high surface area than one big piece with a small surface area, because the higher the surface area, the more frequently collisions will happen on the surface and the faster the rate of the reaction will be. There are some circumstances where this is useful for liquids as well. And the last thing to try would be to add a catalyst. These are specific chemicals for specific reactions that, if they're added, will help provide an alternate reaction route with a lower activation energy. Catalysts do react, but by the time the reaction is over, the catalyst is regenerated, so we see the same reactants and the same products overall. Before we move on to some practice, let's have a quick look at the units for reaction rate you might come across and how to convert between them. For mass, the most common units are grams and kilograms. 1,000 grams is equivalent to 1 kilogram. You can remember this because the K in kilogram indicates 10 to the 3 or 1,000 times. So, to convert from a value in grams to the equivalent value in kilograms, we multiply by 1 kilogram per 1,000 grams. And to do the reverse, we simply multiply by 1,000 grams per kilogram. And we can use the exact same techniques when we're converting between rates in grams per second and rates in kilograms per second. The slightly more tricky thing to convert is the time between units of seconds, minutes and hours, because they will be in the denominator. We know that 60 seconds is equivalent to 1 minute, 60 minutes is equivalent to 1 hour, and therefore 3,600 seconds is also equivalent to 1 hour. So let's imagine we have a rate expressed in grams per second. To get the equivalent in grams per minute, we just multiply by 60 seconds per 1 minute. We need the unit second on the bottom of one fraction and at the top of the other so that they cancel. And what we get is a value that's 60 times bigger with units of grams per minute. This makes sense since if we're making something at so many grams per second, we're going to produce much more of it per minute. So to convert between per second and per minute, we multiply by 60 seconds per 1 minute or 1 minute per 60 seconds. And to convert between per minute and per hour, we multiply by 60 minutes per hour or 1 hour per 60 minutes. And if we want to make the jump between per hour and per second all in one go, we multiply by 1 hour per 3,600 seconds or 3,600 seconds per hour. Let's take, for example, converting 3.6 kilograms per hour into the equivalent grams per second. As the first step, we can convert the kilograms per hour into grams per hour by multiplying by 1,000 grams per kilogram. This gets us 3,600 grams per hour. And then we can convert to grams per second by multiplying by 1 hour per 3,600 seconds, giving us 1 gram per second. And now it's time for some practice. When excess hydrochloric acid reacts with calcium carbonate, carbon dioxide is produced. If 5 grams of calcium carbonate is consumed in 3 minutes and 20 seconds, what is the average rate of reaction? Hydrochloric acid HCl is obviously an acid. And we can see that calcium carbonate, CaCO3, is a carbonate. What might spring to mind is the classic reaction between an acid and a carbonate, producing a salt, carbon dioxide, and water. And indeed, the question tells us that carbon dioxide is one of the products. It's not necessary to answer the question, but I'm going to draw out the chemical equation. Here we have HCl reacting with solid calcium carbonate. I've assumed it's solid because calcium carbonate isn't soluble in water. Our products are the soluble salt calcium chloride, the gas CO2, and H2O in its liquid form. And we'll need 2 HCl in order to balance it. The question also tells us that we're consuming 5 grams of calcium carbonate in 3 minutes and 20 seconds. Our job is to use this information to calculate the average rate of reaction. When we're dealing with masses, the average rate of our reaction is equal to the change in mass divided by the time taken. But we've been given the time taken in a mixture of units, minutes and seconds. So we should convert this all to minutes or all to seconds. I'm going to do it all to seconds. There are 60 seconds in 1 minute, so our time taken is equal to 3 minutes multiplied by 60 seconds per minute, add the 20 seconds, which is equal to 180 seconds plus 20 seconds, which is 200 seconds. So our average rate with respect to the calcium carbonate is 5 grams divided by 200 seconds, which works out as 0.025 grams of calcium carbonate per second. Now let's have a look at the key points. A reaction rate is simply the rate reactants convert into products. Reaction rate is commonly measured by mass per time, for instance grams per second, or amount per time, for instance moles per second. And one of the simplest ways that we can assess the rate of a reaction is to measure the average rate, which is the change in mass or amount of a reactant or product divided by the time taken. And reaction rates are generally affected by changes in temperature, pressure, concentration, surface area, and the presence of a catalyst.